before I start, I'd like to acknowledge that we all meet on the lands of traditional owners. For me, here in Perth, that's the Whadjuk Noongar people, and I acknowledge their leaders, past, present, and emerging as well. So I'm delighted to be able to introduce this HEAT Special Interest Group session today. We've got a really interesting and I think really timely presentation by Professor Ed Wilson from the University of Exeter in the UK, looking at pre-trial value of information analyses to guide trial prioritization and data collection. I've known Ed in various guises for quite a long time. I remember as a very at the very start of my career, I'm catching the train out to University of East Anglia to hear what he's been doing with modelling obesity, and that was I was struck by both his technical skill and his kindness in meeting someone who he'd never heard of before to walk through his model. So 20 years later, I thank you again for that. So Ed is now Professor of Health Economics and Health Policy and Director of PENTAG at the University of Exeter. PENTAG is one of the 11 research units providing expert advice on drugs to NICE. He's got a background from the University of York and holds a PhD in health economics from the University of East Anglia in Norwich. He's worked at York, Cambridge and East Anglia as well, in addition to some time in industry. So he's been on both sides of the discussion, which I think gives him a really important perspective on some of these key issues. He's got experience across a wide variety of disease areas: diabetes, stroke, dementia, obesity, alcohol, lupus, IVF, and so on. But today he'll be talking about a particular focus of his in terms of efficient research design, which is, I think, a really important thing going forward as you know, resources are short and we need to think about how we're best using our time to influence decisions to the greatest degree. So I'll stop talking. I'll hand over to Ed. Ed will talk for Ed. How long do you think your presentation will be?
I think my brief was 30 minutes and then 30 minutes questioning. So
fantastic. So that's what we'll go with. We won't yank you off stage if you run a little long, and if you finish short, that's fine as well. I'm sure there'll be plenty of questions at the end of the session as well. So Ed, over to you.
Brilliant. Thanks very much, Richard, and thank you for that introduction. That was very kind. So what I'm going to talk about, well, welcome and thank you for coming along. What I'm going to talk about today, as Richard said, is pre-trial value of information analyses to guide trial prioritization and data collection. And what I'm going to cover is, first of all, the concept of value of information analysis, so what it actually means underneath it all. I'll cover the key statistics that are estimated in the analysis, which is EVPI, EVPPI, and EVSI. I'm actually going to explain them in a different order. I tend to go EVPI, EVSI, and then talk about EVPPI. That's just my personal preference, but hopefully it'll make logical sense. I'll give a brief overview of how to calculate them. And then I'll really go into what it can be used for, sort of examples of how you can apply it. And then I'll talk about two specific examples where I've used it in the past, and then we'll finish with conclusions and recommendations. Can I just check, is my sound coming through okay, by the way?
Yes, we can hear you fine.
Excellent. I've had trouble. This isn't my usual headset, and I've had a little bit of trouble with my previous one. So if it messes up, please do interrupt and let me know. Don't let me just talk into the void. Okay. So what's the concept? Well, value of information analysis, it's a way of predicting the return on investment from research. And really the value of the information of a particular research project can be thought of as the expected reduction in the expected loss due to uncertainty. Now, what on earth do I mean by that? Well, let's go step by step. The first thing we need is some sort of objective function, something that we're trying to measure and maximize. And incremental net monetary benefit will do nicely in this example. Excuse me. So incremental net monetary benefit we simply get from rearranging the ISA equation. This is the equation. Now, if I should be able to get a little pointer. That's my pointer. So this is the ISA, which anybody who's done any economic evaluation will be intimately familiar with. This is simply the difference in cost between two interventions divided by the difference in effect. We like to use, say, QALYs, quality adjusted life years, as our measure of effect. So we're looking at what's the added cost for every added QALY that we're getting, and if that is below some threshold, which we use the Greek letter lambda for that, then we say it's cost effective. If it's above that threshold, then we say it's not cost effective. Now, what we need to do is we can simply rearrange that, multiply both sides by the incremental effectiveness, in other words, the added QALYs, and what we end up with is an equation that says that the value of the added QALYs has to be greater or equal to than the added cost, which kind of makes intuitive sense. Sorry, it's the wrong way round written, but you'll see what I mean. So we're saying, is the value of what we get more than the value of what we give up? We can then shuffle everything onto one side of the equation, which gives us what we call the incremental net benefit, which is simply the value of the added health gain, the value of the added QALYs, less the added cost has to be greater than or equal to 0. And let's just flip that around to make it to read from left to right rather than right to left. So this is what we call the incremental net benefit. Other thing that's worth noting is that you can further rearrange that into the net benefit of each intervention. So we could have lambda E2 minus C2 is the net benefit of intervention 2, and lambda E1 minus C1 is the net benefit of intervention 1, the value of the QALYs minus the cost. So we can express the incremental net benefit as the difference between the two. This is actually kind of useful because if you've got more than two comparators, then you can simply say our decision rule is the maximum, the option that has the maximum net benefit. So we want some way of estimating the incremental net benefit, and that can be either through a decision model or through a clinical trial. But ultimately, what we'll end up with is some distribution. We'll have a mean incremental net benefit. So I'm using net benefit, dropping the monetary. You can do it with health, the incremental net health benefit, but it's a bit more awkward mathematically. So I'm going to, when I say incremental net benefit, I mean incremental net monetary benefit. It doesn't make any difference. It's just the maths is easier if you stick to monetary benefit. We'll have some process, some analytic process, some data collection process, whatever, economic model, let's say. And we'll end up with a mean incremental net benefit from that, which in this case is about 400 units, which could be pounds, dollars, whatever you want. I think I've used pounds because I'm based in the UK. But because of uncertainty in the inputs into that decision model, there's uncertainty in the incremental net benefit. And that's represented by the distribution. We're going to make our decision on the expected value, on the mean. And in this example, it's positive. So that means we should adopt our intervention 2 in place of intervention 1. But because of the decision uncertainty, i.e. the uncertainty in incremental net monetary benefit, there's a probability that we're wrong. And in fact, the probability that we're wrong is the area under the curve to the opposite side of the y-axis that I've highlighted in red. There's a probability that we're wrong. So if it turns out that we've made the wrong decision, we incur a loss. So the probability of being wrong multiplied by the consequence of being wrong is the expected loss associated with uncertainty. You can then turn that round to say, well, okay, if that's the expected loss associated with uncertainty, that's then the expected gain from eliminating uncertainty. And that's what we call the expected value of perfect information. If you want to see that, perhaps it's a bit easier to understand if you break it down into a discrete approximation. This is the same curve I showed before, but just broken down into a discrete approximation. And you can see that there's about a 39% probability that the incremental net benefit is 250, smaller probability that's plus 750, even smaller probability that's plus 1250. Great. That's the probability we made the right decision. If it turns out that that's actually how the world resolves, then great, we've made the right decision, we've incurred no loss. But there's a probability that we've made the wrong decision. In fact, there's about 20, I think it's supposed to be 22 actually, but it's this got slightly stretched, so apologies. It's a 22% probability that actually we're going to incur a loss of 250. There's a smaller probability, about a 5% probability, that we'll incur a loss of 750, and a small probability that we've got a really big loss. So we can actually work out the expected loss due to uncertainty, and in this case, it's about just under £100, $100 per patient. So what does that mean? It means that we make a decision based on the expected value, but there's a probability that we're wrong. The probability that we're wrong multiplied by the consequence, if we are wrong, is the expected loss due to uncertainty. So that's the expected gain from eliminating uncertainty, the expected value of perfect information. So the next step is to say, well, okay, if there is an expected loss due to uncertainty, is it worth actually resolving that uncertainty? So is a new study worthwhile? So what I've done in this chart, this is exactly the same distribution we had before. I've just squashed it down because I want a bit more room on the y-axis. Now, if we were to do a new study, what do we expect? No, sorry, let's be clear. If I was to do a new study that collected incremental net monetary benefit as its ultimate outcome, so in other words, it's an economic evaluation alongside a trial where we're going to calculate incremental net benefit, and we're going to merge that new study with our prior data. What do we expect that study to generate as its mean result? Well, our prior knowledge, this represents our prior knowledge, so we expect it to give us the same result, because that's our best estimate at the moment. But that new knowledge will give us a bigger sample size, so it's going to shrink the standard error. In other words, it's going to shrink this distribution, it's going to squash it. So we can predict what the result of the study is going to be. It's going to be our prior mean. And then we can actually predict what the posterior distribution of incremental net benefit is going to look like based on the sample size of our proposed study. Because the width, if you like, of the distribution is a function of the standard error of the incremental net benefit. So remember, 1.96 standard errors encapsulates 95% of the distribution. So, and the standard error is simply standard deviation divided by the square root of the sample size. So we can predict what our posterior distribution of incremental net benefit is going to look like. And we could call this the predicted posterior distribution. I think Rafer and Schleifer called it the pre-posterior as a result. And we've squashed it down. So we've reduced the probability of making the wrong answer. So we've reduced the expected loss associated with the decision. So what we've actually calculated is the expected reduction, or what we need to calculate is the expected reduction in expected loss, and that is the expected gain from the new study. And it's actually simply the difference in the areas to the opposite side of the y-axis, and it's actually the area shaded in green here. Now, this is a really bad chart because there's a little triangle just here, and what I should have done is then subtract that off, but that was my bad. It's simply the difference in the prior expected value of perfect information and the predicted posterior expected value of perfect information, which is the green area minus that little triangle there. So a small study will give us a small amount of information. A larger study will give us more information. So we can actually plot the expected value of sample information as a function of the sample size. And we end up with something that looks like this. So it goes up, and actually as the sample size goes to infinity, you will actually find that the EVSI approaches the EVPI. So this is why I tend to explain expected value of perfect information and then straight on to sample information, because the expected value of perfect information is kind of like a study of infinite sample size in that respect. So it eliminates uncertainty. So that's the broad concept. There's a few adjustments to the raw number, and I've realised I've taken way longer than I thought. So I'm going to perhaps skip over a few little things in later on. But I think I'll focus on the examples because they're kind of the more aptly applied. But there's a few adjustments that you need to make to your raw number. Incremental net benefit, incremental net monetary benefit is what I'm talking about, is usually reported on a per patient basis. But you need to scale that up to the relevant population. So you need to say, well, how many patients can actually benefit from the information from this study? This actually depends on the disease we're talking about. So it could be that the prevalent cases of a disease may benefit. So let's say it's a trial for in asthma where it's a new treatment. It could be that all existing patients could actually benefit from that, the information yielded from that trial. Or it might be some other situation where actually the prevalent population can't benefit from it. It's only the incident population. It depends on the nature of the disease and the nature of the treatment. But of course, the incident cases can also highly likely to be able to benefit from this information. But then there's a big question mark over, well, over how long, over what time period are we talking about? And there's no clear answer to that, which is a little bit of an issue with the analysis, and there aren't really any standardized methods. Generally, people seem to say, "Oh, we'll do it over 10 years because that's some sort of proxy for the overall length of time that a decision question is valid before the next big thing comes along," for example. But there's additional factors you can also adjust for, which things like the expected loss for those enrolled in the study, delay before study results reach clinical practice, and so on. There's some fantastic work. It's actually quite a few years old now, but by Willen and Eckermann, looking at that sort of those sorts of issues. So what we do is we've scaled up the expected value of sample information for per patient up to our relevant population. The next logical thing to do is to then compare that with the cost of sampling. And what we tend to assume, rather simplistically, is that there's some fixed cost associated with setting up a trial, and then let's say a constant marginal cost per enrollee. Now it's very simplistic. So I also the way I've drawn this isn't the clearest, but hey, perhaps a more realistic cost function might actually be something like a step function, because it's usually a question of you'll have so many patients enrolled in a study from a center, and then you'll need to set up another center, and so a step function with a gradient along the steps might be more plausible. But it's a question of how detailed you need to go. The whole point of this is to get an idea of the return on investment in the research, not necessarily to get it down to the third decimal place. So we've got the cost of the research, we've got the expected gain. Logical thing, one minus the other is the return on investment. And basic calculus tells us that where the gradient of that curve is 0, is where the return on investment is at a maximum, and that actually then gives us a sample size that maximizes the return on investment. So we've actually used this approach to give us an alternative way of justifying or calculating the sample size for a clinical trial. So it's an alternative to a traditional power calculation. So how do we actually calculate it? It can be quite complex. I'm just going to go over the top line of this because I'm aware of how much time I've used so far. But I said at the beginning that a probabilistic model is usually used to calculate the incremental net benefit. This is the ideal in many ways. You gather information and critically the uncertainty in all of your inputs. So in your decision model, you'll have estimates of treatment effect, you'll have estimates of health state utilities, you'll have estimates of resource use, unit costs, and so forth. Where there is the uncertainty in those, you apply a distribution to those, sample from all of those, shove those numbers into your model, crunch it, and you'll end up with a cost of each intervention and a quality from each intervention. repeat that in the probabilistic analysis 10,000 times, it gives you 10,000 estimates of each of those, or 10,000 sets of costs and qualities. You can then gives you 10,000 estimates of the incremental net benefit, net monetary benefit, and you can plot it as a distribution like that, perform the analysis on that. The alternative is if you've got, say, an existing clinical trial, you can simply do a non-parametric bootstrap of the cost and the quality data from that trial, where you're simply resampling from your observed data, resampling with replacement with an equal number of observations in each arm of your trial. So let's say you had 50 patients in one arm, 55 in the other. You resample with replacement for 50 patients in one arm and then 55 in the other, and calculate the mean cost and qualities. You then repeat that 10,000 times or so, or a large number of times. That gives you your 10,000 or so estimates of the costs and the qualities, and from that you can work out the incremental net benefit, calculate the value of information statistics. I'm just going to skip through the details of calculation. I can perhaps answer questions on that later, but I think it's probably more important just to go through the EVPPI and then just illustrate the examples. So I've mentioned EVPI and EVSI. There's then this expected value of partial perfect information. You may also see it called the expected value of perfect parameter information. Either, it's the same acronym. It's the same idea as the EVPI, but instead of the whole decision problem, it's actually focusing on an individual parameter in your decision problem or a group of parameters. And the way you calculate it is simply with a nested Monte Carlo simulation. So what do I mean by that? What you do, first of all, you pick a value from a distribution of your target, from the distribution of your target parameter, which I've used phi, just because. You assume that's the correct value and then hold that steady whilst you run your probabilistic analysis, so your 10,000 simulations. And I've used psi for all the other parameters because, you know, hey, fancy Greek letters. You then record the expected values. So we've then got one estimate of the cost in each arm, the qualities in each arm, the mean from that PSA. We then repeat the whole thing again by sampling another value from our target parameter and say, well, okay, what if that is the true value? Repeat it again, record the expected values. And then you simply you can calculate the EVPPI in the same way that you calculate the EVPI. I can go into more detail if there's any questions on that. The problem with this is it's quite computationally expensive. So if you do 10,000 simulations in your inner loop for your probabilistic analysis, and then you do 10,000 outer loops, that's 100 million simulations, and if it takes a tenth of a second to do each simulation, well, that's 116 computer processor days. Now, that isn't a problem if you've got access to a high-powered cluster, or, well, you know, Amazon Web Services, and is it Microsoft, is it Azure, Microsoft's version of cloud computing? Easy to access these days if you've written it in a language that is amenable to multiplying and parallelizing across a lot of cores. If your model or analysis is in Excel or, say, Stata, where you would need multiple licenses to have it across multiple cores, then it could be a bit of an issue. There is, however, a handy shortcut. This is a website called Savvy, which is the Sheffield Accelerated Value of Information, which allows you to calculate the expected value of perfect parameter information. It's basically a statistical approximation. And what you need to do is simply you take all of your probabilistic samples, all of your input parameters, and the matched outputs, and it will calculate the expected value of perfect parameter information, the expected value of perfect information for each parameter or groups of parameters as you specify. And you can collect them together in a nice pretty chart here. The value of that is it tells you where the uncertainty, where it's most valuable to eliminate the uncertainty. This was shamelessly copied from the Oxford Handbook's website. I realised I didn't put the acknowledgement in, apologies. So that's the overall principles. In the last 8 minutes I've got left, I'm going to go through a couple of examples where I've used these principles in two relatively recent analyses. The first one was in some work for NICE on guided digital cognitive behavioural therapy for children and young people with anxiety and or low mood. And this was actually a pilot for NICE on what they call early value assessment. And this is where they're trying to identify topics or interventions where it's worth the risk to allow them to be generally available on the NHS whilst further evidence is developed, and then there's a further reevaluation at that point. So it tends to focus on digital technologies in the lay sense, in terms of something involving software or some sort of device. And it's really to say, okay, can we actually, are these promising? In which case, can we just roll them out whilst is there enough evidence at the moment to actually, it's worth the risk to roll it out across the NHS before we've got the full evidence set. So for this case, we had a number of interventions. There were actually four different products that we looked at, and actually 2 of them were for children and 2 of them were focused at adolescents. So it's actually 2 decision problems. And so what I did was to, one thing I should say is these EVAs are very, very tight timelines. We had like 8 weeks to do this entire analysis. And so what I did was to take an existing model, strip it down to the absolute minimum, just do a very, very simple decision tree. I won't go into the detail here, but essentially we had the 4 technologies. We had 3 months of follow-up data for 2 of the studies. I think there was 1 really good quality RCT and then a case study on the other, and then nothing on the others. So this is some pretty bold assumptions required in this analysis. The outcome was this thing called ARCADS, which is a measure of mental health status and well-being. So we took this led lots of other questions, which were, you know, what's the, we don't know what the longer term follow-up, we only had 3-month data, but we want to know, well, what's relapse like and so forth. So the model was really developed with that in mind. We developed some, well, as I say, some pretty heroic assumptions and did a probabilistic analysis on the model inputs. Now, the results themselves, I can show you what the treatment as usual costs, qualities, net monetary benefit, and the confidence interval around those. So that should be credibility interval, I think. The actual numbers, however, are commercial in confidence, because I mean, and also it was actually me that slapped that on, because the analyses were so top line. I didn't want any false, you know, people taking them as gospel. But what I can tell you is that these are 2 of the interventions in children. They were both more expensive than treatment as usual. That's because it was in addition to treatment as usual, so it's the licensing cost and so forth. But on average, there's a small improvement in outcomes, and the mean net benefit for both of them were higher than treatment as usual. They were about the same themselves, though. And then the uncertainty around that was very similar to treatment as usual, just sort of slightly higher. Similar idea in the base case. Oscar was actually quite a bit more expensive. Sorry, in the adolescents, Oscar was slightly more expensive than the others because it was a longer program, but we didn't have the evidence to say whether or not it was more effective. This was actually the only one that had any decent evidence. All the others were really, really sketchy evidence. So I was worried about this unfairly penalizing this intervention. But the key thing to focus on is that the confidence intervals around the net benefit was very similar. So what I did was to plug the results into the Savvy webpage, and it chucked out a cost per, the EVPI and EVPPI per child or per adolescent. And these numbers basically are positive, and it tells you that actually the uncertainty is in the effectiveness and health state utilities rather than the costs. Now, in some ways, that was as far as we went with the value of information analysis for this. In some ways, it wasn't. It was a bit of a no-brainer because the model was written because we had knew we had no evidence on effectiveness. We had no evidence on utilities. The cost data were fairly reasonable because it was based on protocols. So what this actually added, I'm not quite sure. It was just like really sort of an extra adjunct to argue there's a huge amount of uncertainty here, and I guess it just emphasised the fact that it was actually where it was actually utilities that there was an issue as well, not just in the effectiveness. So perhaps it helps in that respect. Okay, last few minutes, I'll go through my second example. This was actually a few years ago where we looked at late pregnancy ultrasound, and basically, an ultrasound scan uses ultrasonic sound waves to generate an image, and it's very common in pregnancy to assess fetal development. And current UK practice was in the first trimester, so the first third of pregnancy, to do a dating scan, what's called a dating scan, which is simply to estimate development, count the number of fetuses there, and you can do a certain amount of diagnostics at that stage as well. The main scan is in the second trimester, which is called the anomaly scan, where there's quite a few potential defects that could be identified and corrective action taken as a result. But in the third trimester, there was only, it wasn't routine to offer an ultrasound scan. It's only where there was some sort of reason where there was a history of the mother had traumatic pregnancies in the past and so on. So the question was, well, actually, is it worth offering this third trimester scan for all? Because I mean, the main driver for this was actually stillbirth rates. I mean, stillbirth rates in the UK are pretty low, but an ultrasound scan is non-invasive, it's very easy, and it's relatively cheap. If we could actually further reduce those stillbirths and other complications of delivery, then that might be a good value investment. So the approach for this project, well, we did several systematic reviews that my colleagues did, looking at different ways you can measure ultrasound, what you can measure with ultrasound, I beg your pardon, and how well those measures predict outcomes. That then fed into the economic analysis, which to say, okay, which measurements and management policies, so what we do once we find an anomaly, are worth it. And then we did the value of information analysis to say, well, how certain are we, and is it actually worthwhile reducing the uncertainty in our knowledge? And there was also a qualitative element, including surveys of recent mothers, and that all went into the recommendations from the project, which was, should we be doing a third trimester screen now, and or should we be doing another study, and if so, what? So briefly, our findings was that the only useful measurements were a presentation scan, in other words, which way up the baby is. So breech is where you come out feet first or bum first. But an ultrasound scan can test that very easily. And also estimating the fetal weight. So specifically if the baby was large or small for gestational age. And they were the most useful measurements you could make, and they were predictors of adverse outcomes. So our analysis looked at each separately at first, but then we merged them all into an overall analysis, which we called the mega model. What we looked at was, so this is a bit of a busy slide, apologies, but we looked at 3 different screening policies. We looked first of all at selective, which is treatment as usual, current practice, only where clinically indicated, where you get a third trimester scan. We then looked at just a quick scan that a midwife could do with a handheld ultrasound scanner. You can get these scanners that just fit in with a USB into a tablet or a phone. Just a very simple presentational scan, see which way up the baby is. Then we looked at actually universal scanning, which is a formal, you go into the clinic, have a full scan measurement of various bits of body parts, and then you can estimate whether the baby's large or small for gestational age. On top of that, so we had 3 different screening strategies. We then had a number of management policies. So what do you do once you've diagnosed an anomaly? Well, actually, there was very little uncertainty as to what you do. If you detect a breech presentation, a baby the wrong way up, you do you can offer what's called ECV, external counterversion, which is where you're trying to manipulate the baby the right way up. That actually happened to me to my mother, I should say, when I was born, and fortunately it was successful. If the baby turns out to be detected as small for gestational age, then my clinical colleague was insistent that you would always induce labour. You would induce early labour because it was considered that the dangers of inducing were lower than the risks of carrying a small for gestational age baby to term. I tried to say, well, actually, is that definitely certain? But my colleague was insistent. However, for a baby that's large for gestational age, there's uncertainty as to whether you should induce labour or whether you should just continue monitoring and go to expectant management, what we call expectant management, and then a normal routine delivery. So what that gave us was actually 6 different strategies, so 3 different screening strategies. The policy, if breech or small for gestational age was detected, you would always induce and offer ECV. But for large gestational age, you could either just hold with expectant management or induce the labour. So we've got these 6 different strategies. So I won't go into detail about the model, but basically it was a decision tree, quite a bit of a monstrous decision tree. But what we found was that overall, it was the option, so this is again, lots of numbers here, but the key thing to come out of this is that the option with the highest expected incremental net benefit was the select a scan just for breech presentation, and then to induce labour if you suspect the baby is large for gestational age. So that came out as the recommended option. But key to this, I've gone way over time, but I'll probably be about another 3 minutes, I think. The uncertainty was huge. There was only a 44% probability that that was the right thing to do. So that then suggests, well, it's worth looking at the value of information analysis. So what did we find? Well, we plugged this into the Savvy software again, calculated the expected value of perfect information. I haven't actually gone into detail about this, but you can calculate EVPI for a range of willingness to pay values, and you end up with a sort of a peak, and then it kind of goes down and then eventually goes up again. But what we found that at £20,000 per QALY as your threshold, the EVPI per mother was £31.56. Well, what does that actually mean? What that means is that on average, we think that our preferred policy of just a selective scan, ultrasound scan for presentation for whether a breech or not, and then if subsequently the baby is detected opportunistically as being large for gestational age, then you should induce labour. On average, that is the best policy. But there's a probability that's wrong. And if it's wrong, there's a consequence in terms of health forgone somewhere, and the value of that health is £20,000 per QALY. So the expected loss when things go wrong is £31.56 per patient, or per mother. So to turn that around, that's the expected value per mother of eliminating uncertainty. That doesn't sound very much, but then when you apply that across the whole of England over 10 years, that turns into £53 million. And something I said is that actually we were focusing on first pregnancies, so nulliparous singleton pregnancies. So first mothers with a single baby. If you assume that you can apply this information to all pregnancies in England, the expected value of perfect information turns to £172.9 million. Now, you could probably do quite a lot of research for £170 million, or even for £50 million. So what research could you do? Well, where is it worth reducing the uncertainty? So we look at the expected value of partial perfect information. And the way I did this was to, first of all, look at every single parameter in the model, and it had this great long list, which wasn't particularly informative. So I divided it into, well, first of all, I eliminated everything where there was 0 value. And that left about a dozen or so parameters in the model. I then grouped those according to what would be logical to measure in a clinical trial or some sort of data collection exercise. It doesn't have to be a clinical trial, it could be a database analysis, a resources, a cost database analysis, whatever. And I divided it into 3. The first one was actually cost of induction of labour, and I'll explain that because this is a bit of a apparently counterintuitive finding. But there's one that was about the cost of induction of labour. Then there was a set of parameters related to delivery of macrosomic babies, in other words, babies that are large for gestational age. And then there was a set of parameters that's related to delivery of small for gestational age babies. So they're essentially 3 studies. And we looked at the value of perfect information for studies. So if you had 3 studies that would give us, resolve the uncertainty in those, what is the value of that to us? Well, it's about £45 million for the cost of induction of labour, 1.2 million for the macrosomia analyses, and about £500,000 for the small for gestational age babies. If you assume that those numbers apply to all pregnancies in England, then the numbers are correspondingly bigger. This was actually really weird because it's a cost of induction of labour. That seems like a really odd thing to come out. When we actually dug down, there was a bit more to it than just the cost of induction of labour. So we sort of looked at it and said, well, actually, it's looking at uncertainty about stage of delivery as well, and also the number of midwife visits, antenatal visits, and there were some other issues as well that kind of made sense. It just says cost of induction of labour. The way it was modelled is a bit more to it than that, so it then made sense. So then we can look at, say, well, okay, there is some value there, but what's the expected value of sample information? Well, I was unable to detect, I actually used an approximation method, but I was unable to detect a non-zero EVSI for the macrosomia and SGA studies, which kind of makes sense because if we look at the numbers, you see you've only got 1.2 million or possibly £4 million for the one study, the study around macrosomic babies, and then between £500,000 and £1.5 million for SGA babies. You're not realistically going to be able to do a decent clinical trial for that. Well, you could probably do one for £4 million, but that isn't going to give you perfect information. That's going to give you resolve some uncertainty. So after having played around with the algorithm a bit, I decided, well, actually, let's just leave it at 0 because looking at the numbers, those studies probably aren't worth doing. But I was able to look at the SI for a study looking at the costings of delivery. And what I found that with a study of about 1,000 patients per arm or participants per arm, mothers per arm, would yield an expected value of sample information of about £11.3 million. And rather than sort of saying, well, okay, what would a study like that cost? I copped out of it actually and said, well, that'll yield a positive return on investment as long as the study will cost less than this. Such a study would probably cost you £4 or £5 million if it was a randomized trial. If it was a database analysis, which you probably could do, it'd be a lot cheaper than that. So this is probably a study that's worth doing. I think, however, the key conclusion was that the outcome studies, clinical trials looking at outcomes are really probably not worth doing, which is, I think, probably the major takeaway. Applications and recommendations then so there's some examples. I've gone way over time. I'll just quickly summarize some applications and recommendations. You can use value of information analysis alongside decision modeling. The EVPPI in particular can show which parameters or groups of parameters are worth investigating with new research. You can actually do a value of information analysis as part of an economic evaluation alongside a randomized trial, which can then help guide future research once you've done your study. Perhaps more pertinently, you can actually do this analysis on a pilot study to inform whether it's actually worth going ahead with the full-scale study, and also to inform which parameters or what data you need to actually collect, as well as the number of observations. Even more so relevant is perhaps if you're doing an internal pilot, you can actually add a value of information analysis as an adjunct to any stop-go criteria you may have. And then the final application really is in a grant application. You want to convince a funder that your study is worth doing. Well, here's an estimate of return on investment from your proposed study. So takeaways then: value of information analysis is based around the idea of expected loss due to uncertainty. Remember, it's the probability of being wrong multiplied by the consequence of if you're wrong is the expected loss associated with uncertainty. Turn that around, that's therefore the expected gain from eliminating uncertainty. We then so that's the expected value of perfect information. We can predict the results of a clinical trial because our prior estimate of incremental net benefit allows us to predict what the results of a trial will be. We can then predict how much the standard error is shrunk by an increase in sample size. So that allows us to predict what the distribution of incremental net benefit will look like after we have collected additional data. Those additional data will reduce the uncertainty, reduce the probability of being wrong, and therefore reduce the expected loss. So that expected reduction in expected loss is the expected gain from that information, or the expected value of sample information. Compare that with the cost of research. That tells you the return on investment, the expected net benefit of sampling, or expected net gain of sampling. You might see it as ENBS or ENGS. EVPPI, same idea, but applied to subgroups of parameters. So it could be just the treatment effect or health state utilities, resource use estimates in your analysis. And the calculations can be sourced from a decision model or a pilot study. It can use it to guide future research directions, estimate value for money for a grant application, and as an adjunct to stop-go criteria for an internal pilot. And finally, there's a few resources to point you towards. This is a recent paper on reporting standards for, it's an extension to the TIERS framework for value of information analyses. This text is just out, well, in the last, I think February it was launched. It's sort of general background to value of information analysis. And finally, there's the Convoy Group website is a useful resource. I'm a member of that group, and it's all things value of information analysis are there. Thanks very much.
Great, thank you, Ed. That was really comprehensive and I think really eye-opening for those of us who kind of dabble in the space. That was just really thorough and really helpful. So thank you. We had a couple of questions in the chat. Connor, did you want to come online and ask your question directly? I'm happy to read it out if not. So Ed, Connor asks, how well developed does evidence for a comparator need to be? Is value of information useful in a case when gathering evidence to evaluate usual care and a proposed intervention is very early in development?
Yeah, this is kind of the catch-22, because one argument is that when you've got absolutely no data whatsoever, you can't do a model, you can't do an analysis, therefore you can't calculate the value of information. And then when you've got enough data to do a really good economic evaluation, you don't need to do the value of information analysis because you haven't got the uncertainty. I think it's yeah, just so your comment, Connor. Yeah, I mean, I take the view that you can always do a model. You can, even if it's only conceptual and top line. That's what I did in the first example with the digital CBT. So I'm not really answering the question directly here at the moment, but you can always do a model. It's a framework to help decision. It is a decision model. I always call them decision models, not economic models. They're there to assist a decision. It allows you to assemble what data you have got and critically to identify the gaps. If you've got a really early stage intervention, well, first of all, there's a question about the comparators. So if you've got treatment as usual, you can draw very heavily on routine data sources. Real world evidence is the buzzword now. I always knew it as retrospective database analysis, but I know in the UK, and I'm sure it's the same in Australia, there's some really, really good routine data available on disease, sort of natural history of diseases, as we've got from routine care. And so that forms your treatment as usual. And then you will have some prior belief about the treatment effect. Somebody is developing this drug because or intervention because they believe it is beneficial. So you could actually put in what you think, just a point estimate of the treatment effect, and critically the uncertainty around that. And there are ways of garnering expert opinion. Again, Sheffield is leader of the pack in this. They've got the SHELF framework, the Sheffield Elicitation Framework and variants of, which is a structured way of talking to experts and trying to gauge their uncertainty about a parameter. For example, a treatment effect in early stage. Does that answer the question? I mean, it could be a no-brainer that we're so you're so early development that of course it's going to be valuable to gather more information. What I think becomes more pertinent is then when you combine that with the price that the manufacturer wants for that, you could help show the trade-off between the price and the effect in your early model, but that's not the same as value of information analysis. What you could do is couple that saying, okay, here's a plausible price for your drug, and this is the value of additional information.
Great, thanks, Ed. We've got a couple of questions just before we sign off. So one from William and one from Karen, but the ACTA team will have to unmute people one by one because we're still learning how to deal with WebEx.
Can you hear me?
William, yes, we can hear you well, yeah.
This is a really, I think it's a continuation of the question that Connor asked, but it's from a real world example. I'm involved with some colleagues with a pilot study of an intervention in labor, a drug. And we have some pilot data from a 300 patient study in which the intervention was associated with a 3 out of 150 rate of admission of the baby to the neonatal unit, and the control the intervention was associated with a 5 out of 150 rate of admission to the neonatal unit, and the control 3 out of 150. The relative risk for that is 1.67 with a confidence interval, 95% confidence interval of 0.41 to 6.8. And is it reasonable on the basis of that tiny number, that tiny pilot study, to assume that the truth is that the intervention really does increase neonatal admission by 67% when the clinicians think that that result is clinically implausible and the confidence intervals are incredibly wide?
The way I would handle that is I would propagate that uncertainty through the analysis, an economic analysis, to say, well, okay, what does that actually do in terms of cost and health outcomes? And then say, well, okay, we don't believe that. Is it worth reducing the uncertainty? So you could do a value of information analysis looking at that parameter. I suspect, I don't know the full situation. Is that your primary outcome?
No, no, it's not. No.
Okay, it's just an observation that you found. It's associated with it. Okay, okay.
Yeah. It's a component within a composite primary outcome.
Okay, I mean, my approach is just to bung that into your analysis. What sort of economic analysis are you doing? Have you got a formal structured economic model around this?
Yes.
Okay.
This is very similar to what you showed, and I mean, I'm not an expert in this. I'm working with my colleagues.
Okay, I would say that's the uncertainty. They're the plausible bounds of uncertainty. We can't say yes or no there is an effect on admission to, was it NICU?
Yes.
Said, yeah. We can't say there's an effect, but what we want to know is what's our best estimate. Our best estimate is that actually it's an increase, but we could be wrong. propagate that through the economic analysis, and then do a value of information analysis to say, okay, do we need to, is it worth exploring, gathering more research to reduce the uncertainty in that? I suspect it's a bit of a no-brainer situation. It's like, okay, this is a huge confidence interval, therefore it's probably affecting the results a lot. So I suspect a value of information analysis would say, yes, we need more research here.
Okay.
Does that answer your question? I'm not sure I have, but
no, it's a step along a journey. Thank you very much.
Yeah, I think the way I was take it very much, you've got a parameter, a distribution around a parameter. That's the uncertainty you've got. You propagate that through your analysis. You should really be analysing models probabilistically. I think PBAC aren't so convinced about probabilistic analyses. Am I right in that? And the deterministic analyses tend to be more common in Australia. Is that correct? Or yeah. You really need the probabilistic analyses, but yeah, it's just propagating that uncertainty through. You say, here's, given all the evidence in terms of the economics, this is our best estimate of the results of the cost effectiveness, but here's the uncertainty around that. Is it worth reducing that uncertainty? That's where the value of information analysis comes in, and it'll tell you where there's greatest value for reducing this uncertainty, where you should focus your research efforts.
Thank you very much.
Thanks, Ed. So I'm aware we're on the hour now, so if people need to head off, please feel free to head off. We do have time probably for, if we can indulge you, Ed, for one more question. Karen, did you want to come online and ask your question of Ed?
Can you hear us?
Yes, we can, yeah.
Oh, okay. Hi, it's Rachel and Karen here. Apologies for not being able to log in earlier. Ed, I had a question about implementation. So there's some assumptions about if you were to apply this across the population, then you're assuming that most people are going to take up the intervention. How do you vary? And in actual practice, you have a positive trial, but not everybody does change and do what might be recommended even in clinical practice guidelines. So what's your approach to modelling the proportion of uptake or implementation?
There's two ways you could look at this. The implicit assumption in the analysis that I've presented is you get 100% uptake. There is actually a separate literature on the value of implementation, because it could be that we know what the right thing to do is. In other words, we have a systematic review, economic evaluation that says what the right thing is to do, but nobody's doing it. So therefore, you actually need to invest your efforts in getting the message out there and banging the drum, saying this is what you should be doing. And so there is a literature on the value of implementation. The other alternative is to simply add in uptake in your economic model. And actually, there was a little bit of that in the ultrasound screening work, where when a breach presentation is detected, we had the intervention was offer of an external counterversion. Not all mothers want it. It's pretty brutal. It's, you know, it's not pleasant. I think there's worse things, but so not all mothers will opt for it, and we've included uptake of the intervention in that, and also the consequences. So if they turn it down, then you can either have an elective cesarean, or if you turn down an elective cesarean, there's a risk of emergency cesarean in the actual, when it comes to labour and so forth. So so in principle, you can include that in the economic model. And then you could actually look at uptake as a parameter and work out the value of increasing uptake.
Great. Thank you, Ed. That was really clear. We're a couple of minutes over time, so unfortunately we're going to have to draw it to a close, but I hope if anyone has any further questions or thoughts, that they're happy to reach out to Ed directly, because I think it's a really interesting topic, and it's not one which has been engaged with as broadly in Australia as it has in the UK, and I think that's probably to our detriment. So your expertise has been really valuable today, and really helpful for me, and I'm sure for the rest of the audience. So on behalf of the special interest group, I'd like to thank you, Ed, for speaking to us today and sharing your expertise. It's been, as I said, massively valuable. So thank you very much. And to everyone else, I hope you have a great evening, and look forward to seeing you at the next workshop. So thank you, everybody.